Now, what do we actually have today? In what sort of proportions were these elements formed? Now, one way to see that is to look in detail at the sun, the solar spectrum, that we can analyze in detail. We have very high signal to noise of that. Another way is to get some material. And of course, ideally, we would like to fly into space and take a little bit of material there and analyze it, bring it back to Earth and analyze it in great detail. But that is not yet what we can do. Instead, what we do is actually analyze the meteorites that fall on Earth and look in detail at their composition. And it turns out that the composition of those meteorites is very, very similar to what we have actually in the sun. Of course, the volatile elements have been lost, but those we know how much they are. And that then ends up with a very famous plot from 1956 from Harold Urey and Hans Suess about the cosmic abundances. And you see, this is all normalized to silicon at 10 to the 6. You see, of course, the overabundance of hydrogen and helium, and then for certain peaks in these abundances. And again, this is very similar to what we also find in the sun, where we can measure the elements. Now, what explains this trend in all of these abundances over 12 orders of magnitude? It's basically the shell model of the atoms that was started, obviously, already with Mendeleev. And so we actually have here the magic numbers, 2, 8, and 20, that are very peaks in abundances. Iron, very important element, the highest binding energy per nucleon. That's why it's such a peak there. And then you get a few other peaks that you see indicated over there. And so here we go from meteorites actually to nuclear physics. They tell us something about that. In fact, we can go one step further from nuclear physics to actually nucleosynthesis. And this goes back to a very famous paper from 1957, B squared FH, it's called, as to how the various elements were formed. The burning of hydrogen and helium, basically leading to carbon, oxygen, nitrogen, neon, etc., makes the lowest elements. Then iron, already explained, that's a peak in terms of stability. And then beyond iron, we get into elements that are primarily made through neutron captures. That plays a large role in there. So this is what we can actually now also observe in space. This is a beautiful image made. It's a composition from data from the Chandra X-ray satellite and also the New Star satellite, a very recent satellite. It shows you the supernova remnant, Cassiopeia A. And what you see in the different colors is basically images in the X-ray lines or of these various elements. So silicon, magnesium, they all have their specific lines. Is in green. There you see them being produced. Iron you see being produced in large amounts, and then also here 44 titanium actually being produced in this particular case up to a fraction of % of a solar mass that is produced in this one supernova. So here we can see actually sort of element production in situ actually happening at this very time. Now, if you go beyond iron, then indeed the proposal was always that this would be done through neutrons, and that neutron-neutron star mergers would play a large role in it. A neutron star is one of the densest possible stars that you have, collapsing at the end of a stellar life, as much material of the sun in an area that is probably as big as St. Petersburg. So huge densities, and when they merge, that is actually where you have the conditions, lots of neutrons in order to produce gold. And this was actually, this gold rush was actually confirmed just very recently when one of these neutron-neutron star mergers was actually detected by the gravitational waves from the LIGO-Virgo collaboration in 2017. Then they also took spectra of this event, and they saw the signatures of all of these elements beyond the iron peak that were actually produced here in this neutron-neutron star merger. So for this particular event, produced several oceans in terms of mass of gold in just this one neutron-neutron star merger. Good. So that's a brief summary of how we make the elements in space. And again, if you want to hear more about it, please come to the symposium or look in detail at the poster that you see over there. I now want to switch more to chemistry. What can we actually do with these elements in space? Because space is actually very empty, it's very tenuous, it's very cold, and so chemists would expect that there is actually nothing happening there, that you just have the elements there. Moreover, we have this overabundance of hydrogen, this carbon, nitrogen, oxygen, the elements that we are actually interested in making organic molecules, for example, present at only a fraction of a promille. So, how do we go about, how and where do we actually go and search for molecules in space? Well, this is an image that may be familiar to some of you. It's the Orion Nebula that you can see on a clear night, also here from St. Petersburg. If you go to the sword of Orion, there's a little telescope, you can see the Orion Nebula. What you see here is this beautiful reddish glow, and that is, makes it so colorful, this nebula, but that's not the gas that we are interested in. That's actually the ionized gas, 10,000 degrees. That's too hot for molecules. We see here basically the H-alpha recombination line of atomic hydrogen. What we are interested in is these very dark regions that you see here. Oops, if you follow my, yep, there you can just see the pointer up there, these very dark regions in this optical image. And they are so dark because they contain these tiny little dust grains, little dust particles that actually absorb and scatter the light and make it look very dark. Now, this image also shows something else, namely the fact that this is not just a chemical factory, as we will see in a moment, but this is also actually a nursery of new stars that are being born at this very moment here in the Orion Nebula. That central part that you see over there contains thousands of young stars meaning only 1 million years old, not yet a few billion years old, like our sun is. And in fact, it was Victor Ambartsumian, who I think was here at St. Petersburg State University and also at the Pulkova Observatory, that made this very important point. Up to the sort of 1950, people thought that stars were part of cosmology, that stars were there eternally. They did not think that stars could also be born and that stars could also die. And it was Victor Ambartsumian who made a very important conclusion, actually, by looking at a certain type of stars and looking at their distance from the clouds, like the Orion Nebula, that he said, you know, stars do not have eternal life. Just they also are born and they also die again.